Hello everyone, welcome back to Civil Engineering Progress. In this video we're solving statics problems involving a pulley and a cable system. So we are given that a load Q is applied to the pulley C, which can roll on the cable ACB. The pulley is held in the positions shown by a second cable CAD, which passes over pulley A and supports a load P. The angle between segment AC is beta 55 degrees and the angle between segment CB is theta 25 degrees. So knowing that P equals 750 newtons, we're gonna determine two things: the tension in cable ACB and the magnitude of load Q. So first, I'm gonna try to explain a little bit what all of this text means with the pulleys. So if we zoom in a little bit, we can see that this pulley goes around goes around the pulley to B. B is a pin, so it doesn't move from there. This one is also a pin over here, so it doesn't move over there. And here it is around the pulley, so here this pulley can move freely around here, depending on the weight, of course, on the weight of P. And P and Q are directly related in that P here is loose in this pulley that can pull in and back this C pulley, and depending on the Q weight the weight is kind of like tied in here, so it holds this piece of the pulley in place. I don't know if I could explain it clearly, but the way we are gonna solve the tension in cable ACB is by doing a free body diagram. But before that, we will be assuming the pulleys are frictionless. And we already know some information about pulleys. One is that the tension is the same, and they are small enough that we just do particle. Equilibrium. So this is some given information that we already know about pulleys, and so now we're gonna go on to solve the problem. To solve this problem, we're gonna do a free body diagram of this section. Since we're interested in A, C, and B, we're gonna do this section. And we're gonna kind of look at the image there and try to replicate it in here in the particle equilibrium way. So the pulley is a dot, and then we have our y and x coordinates, and then we're gonna add the forces, which is this force going down, which is Q. So we have a force going down and it's Q. Then we have a force going this way, which is the cable that we're interested in. So it's going this way. This is theta, which is 25 degrees. And this one, we're gonna call it TACB. and then the other TACB is gonna go this way. And the reason why we're calling it the same is because when you have a pulley system, the tension in either side of the pulley should be the same. So we will assume that in this case. Now we still have one more force here, which is the force AC, this cable that's going down. But since in either side of the pulley the force is the same, we can call it force P, because that last force will be the same as P. So we're just gonna call it force P. And I'm gonna make this one a little bit more up because I feel like it's too far down. TACB. Okay. So this angle is 55 degrees. Okay, so now we have the free body diagram and we can solve it. So we can form our equilibrium equations. So the way that we're gonna solve this is that we will do our equilibrium equations in the sense that all our y components of this body diagram equals 0, and all our x components of this one also equals 0. So we're gonna start with the x forces. So the sum of fx equals 0, and here we're gonna use the x component of TACB, which it has two. One is related to the 55 degrees and one is related to 25 degrees. So one is going to the negative side of x. So this is the x-axis. This is our 0 point of the x-axis, and one is going negative from 0 and the other one is going to positive of 0. So we're gonna take into account those symbols. And so to take into account this one, we're gonna use the SOHCAHTOA, the TACB in the left, we're gonna use the SOHCAHTOA to find this part. So we don't know TACB, we only know the angle. So we're gonna use the TACB and we're gonna multiply it by the angle cosine of 55 utilizing the SOHCAHTOA. It is to find the adjacent, is adjacent over hypotenuse, and we have the angle, so we pass the hypotenuse over to the angle. Let me illustrate it here. So cosine theta equals opposite over hypotenuse, which here the opposite is, hold on, it's adjacent, sorry. Here the adjacent is the x coordinate and our hypotenuse is TACB. And so if we pass TACB over to the left, multiplying it, then that's our x coordinate. So that's how we got that, and then it is negative because again it's going to the left, not going to the right. And so now we're gonna subtract 750 cosine of 55, and this number is for our P over here. For this other negative component of the P, it's hard to see, but this p has also a negative component, so in total we have 3. And this one, we said before that, if you recall, p is 750 newtons, so we're gonna take 750 times cosine of 55, also using the same reasoning we used before with the SOHCAHTOA. Now we're gonna do TACB, the positive components of this, so we're gonna do plus TACB, but this one has a 25 degree right here, so we're gonna utilize cosine of 25 degree. Again, the cosine is because this one is the adjacent, and we're doing hypotenuse over times the adjacent, hypotenuse over adjacent, and then we multiply it by the cosine of the angle, if it makes sense. So all of this equals 0. I'm gonna make it smaller real quick so we can fit our numbers nicely. And here we're gonna solve for TACV. Here we have all of these in terms of ACV is our only unknown, so if we distribute everything and calculate the result, we get that TACV is equal to 430.18 of this. So now we're gonna solve for Q. So here it asks us to solve for Q. To do this, we're gonna do the sum of forces in the y direction, and for the y direction we have Q, and we have this one that we didn't know what it was before, but now we know it. Now we know what this one is, and we know this one as well. At least we know enough to be able to solve for it. Okay, I'm gonna say TACV sine of 55 degrees plus 750 sine of 55 degrees plus TACV sine of 25 degrees minus Q equals 0. We just say minus Q because Q is directly going down, so it's already in the y direction. It has no x portion. So if we distribute everything and plug it into our calculators, we would get Q equals 2,220 newtons going down. And in case I didn't mention it before, the reason why we started here with the x coordinates is because Q doesn't have any x coordinates, and it would be, if we started with the Q and not the, if we started with the y and not the x, the y has Q plus it has TACV, so we would have two unknowns, and that would make it a lot more difficult. So when you see the problem, you have to see what makes my calculations easier. So in this case, TACV was the same, and so we can make everything into terms of TACV, and we knew P already, so that's why we started with the x directions. Okay, and then now that we have TAC, we can go down to Q. Also, here I just wanted to explain real quick the reason why these both angles here were 55 degrees, so that over here you can see that these are both parallel to each other. So that means that the angle here is the same angle over here as well. And so I think that concludes what our problem is right now. And let me know if you have any questions and if there's anything I can help with. Thank you for watching.